So today we are talking about the margin of error, and the margin of error is the max expected difference between, and then leave a little space for the formula, but I didn't leave you guys enough to write here. So the max expected difference between the true population parameter and remember, a parameter is just a number that describes the population. It could be the mean, it could be the standard deviation, it could be something else. So we're saying this is the maximum expected difference between something that's actually true of the population and the sample estimate of that parameter. So since we are not typically able to actually test the entire population for something, then we test a sample and we come up with a mean that describes that sample. Well, that mean is probably not perfectly accurate. It is accurate to a certain extent. And so when we say the margin of error, we're going to make a guess as to how far off that answer that we got based on the sample could be when you compare it to the population. Okay, so we'll say it's probably the mean within 5. Could be 5 above that, 5 below that. That's about what the mean should be. It could be that 20% of the people said this, but really it's probably not exactly 20%. It's probably between 18 and 22% because there's a margin of error there. Does that make sense? Okay, so the formula that we're going to use, and this is very simple. If you were to take AP statistics, this would get all sorts of crazy with lots of different ways to calculate it. Nope, we're not interrupting because you're going to kill a wolf. Thank you. So the formula is 1 over square root n. Statisticians have 95% confidence in the range you get as a result of this margin of error. So they're going to say 95% of the data that you find is going to fall in that range, but extremes are not included. So things that are extremely one way or the other, probably not included in this, but 95% sure that our numbers are going to be accurate. All right, we're not going to mess around. Stop. We're going to let me get through the notes. Stop acting like a child. Both of you, stop it. All right, for example, 900 American teens were surveyed about their favorite ski category in the 2002 Winter Olympics in Utah. Ski jumping was the favorite of 20% of those surveyed. So we want to see if that 20% applies to the population, like what answer was probably true if the entire population of American teens was surveyed. So if every single teenager in America was asked that question, would it still be around 20% or could it be higher or lower? Does that make sense? Okay. So we're going to say the margin of error is probably 1 over the square root of 900. Let's go ahead and figure out what that is. Yep, it's 1 over 30. And so on, right? Lots of 3's. And if I take that decimal and I convert it into a percentage, how do I convert that decimal into a percentage? Okay, so this is about 3%. It's really 3 1/3%, but we're just going to call it 3%. So for the sample, 20% of teens said that their favorite was ski jumping. If we were to apply this information to the entire population, we would say that it's probably somewhere between 17 and 23% for the entire population. It could be 20, but it could be 19. It could be 22.5%. Could be anything between 17 and 23. And we are 95% sure that that's the right answer. Yes?
How do people make up this equation to find out?
That's a great question for Google. All right, next page. Find the margin of error if they had 100 American teens. So we're going to do 1 over square root of 100 which is 1 over 10, which is 0.1, 10%. So if they had only done a survey of 100 teenagers and found that 20% was their result, then we would have said, okay, between 10% and 30% of the entire population probably agreed with that, would have had the same results. So 20% is what we got for our survey. We said 20% of teenagers preferred ski jumping as their favorite event. So if it had only been 100 teenagers that were surveyed to give you that result, then we would have said the likelihood that that result was true for the entire population would have been anywhere between 10 and 30%. So it's a lot less accurate when you have a smaller sample. Okay, now let's say we have a bigger sample. We have 9,000 teens that are getting that survey. And what percent do we have here? About 1%. So if the original situation had said that they surveyed 9,000 teens, and that of those 9,000 teens, 20% of them said that ski jumping was their favorite, then we would say, oh, with the population, we have a 19 to 21% of the entire population that would have that same as their favorite. So when we have a bigger sample size, our answer gets a lot more accurate. All right, what if we had 90,000 teens? One divided by 300? Okay, and what percent is that? 0%. Technically, it's 1/3%, right? So that would be like, you're pretty much spot on at that point. You have a big enough sample size that we think that this sample really is representative of the population. Because 90,000 is a pretty big sample. Okay, so we would say, really, you're probably right there around 20%. Okay, so what's your conclusion about finding the margin of error based on the size of the sample? Yeah, the bigger the sample size, the smaller the margin of error, which makes sense because the population is everyone, right? So when your sample gets closer and closer and closer to being everyone, your answer becomes more representative of everyone. If you have a sample of 2 people, that's not as accurate as a sample of 1 million. A sample of 1 million would be fairly accurate. Yeah. All right, so take a moment, write an answer to number 4 in your own words. I should see you writing. No, the margin of error is like how accurate you are. And so we noticed that when we had 100, our margin of error was 10. When we had 9,000, it was 1%. That was good, right? That means our answer is getting like closer and closer to being more accurate. When we had 90,000, our margin of error was like less than 1%. So the bigger your sample size is, the more accurate you are, and the smaller your margin of error. So we like a small margin of error because that means our chance of being wrong is less. Right, because error, right, margin of error. Okay, someone give me a percentage that's an even number. 18. Okay, so we're going to say 1 over square root n equals 18%. So if you want to cut the margin of error in half, so we're going to say 1 over square root n equals 9%. Okay, so if we want to cut the margin of error in half, what do we have to do to the sample size? So what we're going to do is we're going to figure out what sample size gave us 18%, and then we're going to figure out what sample size would give us 9%, and we're going to see how much bigger the sample size has to be to cut it in half. Okay? So I need to solve for the square root of n. So right now I have 1 over the square root of n equals 0.18, because that's how I write 18% as a number. So what do I do now? I wouldn't square it just yet. Move the square root of n over to the other side because it's on the bottom of a fraction right now, and that's not helpful. So I've got 1 equals 0.18 times the square root of n. And then what? Divide by 0.118, right? Because it was multiplied, so we got to divide. And then what would I do? Square, right? Undo the square root by squaring. So 1 over 0.18 squared. Okay. Okay. So that's about 31 people. Okay. Over here, we've got 9%. So I've got 1 over root n equals 0.09. And then 1 equals 0.09 times the square root of n. Over 0.09 equals square root of n. Square root. Okay. What do you notice? It's 4 times as much. So if you want to be twice as accurate, if you're cutting the margin of error in half, you're getting more accurate, right? To cut the margin of error in half, you have to quadruple your sample size. To cut the margin of error in half, what do you have to do with the sample size? Quadruple it. And we chose 18% and 9%, but we could have done it with any. We could have said our margin of error, we want it to be 50%. So then what would you have to do to get it to 25%? You'd quadruple it. Okay, so any number you chose would have worked. Quadruple the sample size. Yeah, so the 31-ish is the sample. And then we would need to quadruple the sample. Okay, so how large would the sample need to be for a margin of error of 5%? What do we do? Yeah, the same thing we just did. 1 over square root n equals 0.05. How large of a sample would we need for 2%? 1 over square root n equals 0.02. Do we need to show all our steps, or can we kind of jump to the end? Jump to the end. Well, these are both exact answers. So for 5%, how big does our sample have to be? 400. So depending on what we're testing, we could need 400 people to be surveyed. We could need 400 dogs to be observed. We could need 400 cookies to be weighed. We could need 400 grandmas to be smiled at. That's a cute one, isn't it? All right. The last, I'm not going to erase because my eraser's terrible, is how many? 2,500. So 2,500, whatever would need to be the sample size. All right. Wasn't that a good time? We've learned all the things. All right. So I have a worksheet for you. It is like the easiest thing we've done all year. Okay, it's fairly quick. So I'm going to go ahead and hole punch this, hand it out. So the plan for today is